the second day of video notes for Unit 7, and today we are looking at integrating composition functions. Up until now, when we've been doing integrating, we've been looking at sums, we've been looking at constant multiples, we've been looking at stuff that's kind of easy to integrate. We'll see in just a second that we don't have a product rule or a quotient rule or a chain rule for integration. Right? So let's look first at a couple of integrations that we know how to do that are pretty straightforward. If we want to integrate x cubed, it's pretty clear to see that that is going to be 1/4 x to the 4th plus c. If you want to integrate cosine of x, pretty clear to see that that is going to be sine x plus c. And if we want to integrate this here, 8x cubed plus 3 cosine x. So this is a sum where you use the term rule. The term rule works just fine for integrating. This is going to be x to the 4th, which then means when we take the derivative of x to the 4th, we'll get 4x cubed. We want 8x cubed, so then that means this coefficient must be 2, and then the antiderivative of cosine x is sine x, and we want the coefficient to be 3, and then we put our plus c. All straightforward. Now here, D, things get a little bit trickier. Well, let's work with the cosine x. So the antiderivative of cosine x is going to be sine x, and then the antiderivative of x to the 3rd, that would be x to the 4th, and to get the coefficient right, we'd put the 1/4. So we might think that that would work for us. But then if we were to take this and find its derivative, in order to find its derivative, we would end up needing to do the product rule. So we'd have the derivative of the first times the second plus the derivative of the second times the first, and there's no way that that's going to end up looking like that. Right? So that doesn't work for us. Something like this, right? So D here, this is a product, and we're trying to integrate a product, and we failed in terms of integrating a product. Here we have a composition. We have one function inside another function. Right? So if we just start attempt number 1 at integrating this might be the sine of x cubed plus c. But then if we take this and find its derivative, we should get back to cosine x cubed. Well, to do the derivative of this, we're going to take the derivative of the outside function, which is cosine x cubed. That's good. But then we're going to end up needing to take the derivative of the inside function, which would be 3x squared. And there is no 3x squared up here. Right? So that doesn't work for us, because we need to have a 3x squared here. But perhaps if we were to take attempt number 2 here, the sine of x cubed, let me move that over, sorry about that. The sine of x cubed, we'll start with that, and we know that when we take the derivative of this, we're going to end up with 3x squared, but we don't want a 3x squared here, so perhaps we could take all of this and divide it by 3x squared, and then we would just throw on our plus c. Right? So this seems like a logical second attempt, but if you take this and take the derivative of this, attempting to get ourselves back here to cosine x cubed, now you have the quotient rule, and you need the derivative of the derivative of the first times the second minus derivative of the second, and that is not going to get us back to, it's not going to simplify out to be cosine x cubed. So this doesn't work, right? So what we've just seen is that integrating products, integrating compositions is tricky, if not impossible. So let's look at a few more down here. So if we try to integrate this, the quantity 3x minus 7 raised to the fifth, we are going to want 3x minus 7 to the sixth, and then we'll have a 1/6 in front, plus c. And now if we think about this, when we take the derivative of this, the derivative of the outside function is going to be 3x minus 7 to the fifth power. We're going to multiply the 6 times the 1/6, which will get us to be 1. That's fine. But then we have the inside function, and the derivative of the inside function is going to end up being 3. So in anticipation of that inside function's derivative being 3, out here we're going to add in a 1/3. Right. So then the integral here would be 1/18. Right, so let me just change this to 1/18. Right? So that worked. We were able to deal with the inside function. Right, so let's try that again, see if this will work over here. So we start with the outside function, the integral of the outside function, which would be 6. This is going to be 1/6. And then the inside function, the derivative of the inside function is going to end up being 6x. So the idea would be to divide by or multiply by 1/6x. And even though it's not going to work, I'm going to throw the plus c on there just to stay in the habit. And you can see now, if this truly were the integral, when we take the derivative of this, we would end up again needing to use the product rule. This here would be our first function, which is going to end up being 1/x, and then this would be the second function, so the derivative of the first times the second plus, and that's not going to get us back up to here. Right? So that doesn't work. All right, so let's look at this one. So here we have a composite function that requires some sort of chain rule undoing to work with. This is a composite function, one function inside of another, and in addition to that, we've got this 6x up in front, which on first inspection might look like it's even more difficult. But if we again go through and give this a shot, you will notice that we've got 3x squared minus 7 raised to the sixth. We would have a 1/6 here, a plus c, and then notice what happens. If this is the antiderivative, if we take the derivative of all of this, we would want to get back to here. And notice that the inside function here, the derivative of the inside function here, is going to end up giving us the 6x. Right? So what originally looked like it was really complicated, even more complicated, turns out to be a blessing in disguise, and we really like the fact that we have this 6x. Right? And this right here is indeed the integral for 6x, the quantity 3x squared minus 7 raised to the 5th. All right, next problem. D. So we've got the antiderivative of the cosine, which is the sine. So this is going to be the sine of 5x. When we work this the opposite direction, take the derivative of this, we're going to end up with cosine 5x times the derivative of the inside function, which is going to be 5. So in anticipation of that, we put a 1/5 out in front. Right? So this is the antiderivative for cosine 5x. E, same idea. We're going to do the sine of x to the 5th. But now what we have is when we take the derivative of all of this, we're going to need to use, we'll end up using the chain rule, and we're going to need to have, you will end up with an x, a 5x to the 4th. So the idea would be perhaps we could divide by 1 over 5x to the 4th, and everybody already knows that that is just not going to work, because in order to take the derivative of all this, you're going to need the product rule, and the product rule is not going to get us back to where we need to get to. All right? So this one fails, but its neighbor, f, has got the x to the 4th sitting right here, waiting for us. Right? The x to the 4th is the derivative of the inside function. So the derivative of the inside function is a version of x to the 4th. Right? So this is just a 5th of the derivative of the inside function. So this one is looking hopeful. So we have the sine of x to the 5th plus c. When we take the derivative of this, we will get an x to the 4th, but we're going to end up getting 5x to the 4th. So we're going to want to put a 1/5 out in front. Right? So this is the antiderivative for x to the 4th cosine x to the 5th. All right, moving on. G. So 4x plus 2. This is going to be -2, which means that to get the coefficient right, we're going to need to have a -1/2. And then we're going to need to deal with the derivative of the inside function. So the derivative of the inside function is going to go right there, and I haven't given myself enough room for that, but we'll just tuck it in here really small. So that's going to be to take care of, to get the coefficients to work, the derivative of the inside function is going to be 4, so we put a 1/4 out here, and final answer is -1/8 4x plus 2 raised to the negative second. Alright, so you should have noticed by now that it's this right here that makes or breaks whether or not we can take the integral. So what we're looking for is we want the derivative, or some version of the derivative of this, of the inside function, to be sitting right here. Right? So if we have anything, if we have something that is in the form of x squared, then it'll work, right? And even better yet, would be 12x squared. Because when you take the derivative of 4x cubed, you're going to get 12x squared. Right? But we're going to just work with x squared right here. And we'll do the antiderivative here. And you should be noticing, you should be getting more comfortable with doing these. This is going to be 4x cubed plus 2 inside function to the negative second, negative 1/2 out in front to balance the coefficient. Put our c on the end, and then we're going to need to get a 1/12 to balance the coefficient of the derivative of the inside function, which means when we're all said and done, we have negative 1/24 4x cubed plus 2 raised to the negative second plus c. Okay, last one. Blank here, we want to figure out what would be nice to have in here. What would be nice to have in here is the derivative of sine x. Have that waiting for us. So we're going to put in here a cosine x, and then the antiderivative becomes quite straightforward. This is sine x to the minus 2 plus c, and then we just have to balance the coefficients. So this is going to be a minus 1/2 in front. Alright, so we're done with the front side of today's notes.